Now we have Professor Wojciech Samek, and he's such a humble person that I have to introduce him shortly. He's a professor at the Department of Electrical Engineering and Computer Science at TU Berlin. He's also jointly heading the AI department and explainable AI group at Fraunhofer HHI. You studied computer science at Humboldt University 2004 to 2010. You were a visiting researcher at NASA. Wow. And a 2014 TU Berlin PhD at age 29. And what's really important about Professor Samek is you have so many best paper awards, many of them highly ranked in the top 1% in the field of engineering, that you are apparently really a man at the top of your game, and not just as a serial knowledge entrepreneur, but also, I hear, as a serial dad. So congratulations on that again, Wojciech. And yeah, like children growing up, AI has come a long way from asking how is a horse, and you had this leading publication in 2015, you should really check it out, with your team's layer-wise relevance propagation, LRP, revolutionizing, I would say, the field of XAI, and now you're pursuing it again with XAI 2.0, so asking not just according to which pixels does the AI know it's a horse, but why does it know it's a horse? Wojciech, you're involved with so many things, IEEE, bifold, over to you, and thanks so much.
Thank you very much for this kind introduction. Yeah, today I'm very happy that I always try to present you some of the new developments which we did over the year, and today I will present you kind of work of two papers which we published in the last year. One was published at Nature Machine Intelligence and the other at NeurIPS. So colleagues are now went over to NeurIPS to present it. It's basically about new types of explanations. So we want to get a deeper understanding of what's going on. And basically what I always tell to people is that you could imagine kind of these two different words. One word is a human-built system, such as airplanes. They consist of millions of components, highly complex. But in this case, we know, like engineers know, the quality of every component. So every screw in an airplane has to fulfill certain norms, has to be temperature resistant, and people are able to evaluate and test not only individual components, but also the interactions of these components, so that we are able to test the system and know and kind of ensure that it behaves as intended. On the other hand, we have modern AI systems such as LLMs with less components, but these components are interconnected in a more complicated way, and where we don't have this state of knowledge. We don't know exactly what individual components are doing. We don't know the effects of what happens if one of these components will be deleted, so we don't have this kind of understanding. And what we want to do with our explanation techniques is to bring like the black box nature of AI models more closely to this vision which we have when dealing with engineered systems. And the one practical example where this can be important is, for instance, in an AI system which deals with skin cancer prediction. So when you have been to a dermatologist, you maybe know that there is this ABCDE rule in dermatology. So if the dermatologist is scanning your Navi, it may look at this how asymmetric it is, whether it has like sharp borders or blurry borders, whether the color distribution is uneven or even. And this kind of rule of thumbs helps the medical specialist to at least guess whether like a potential melanoma is really cancer or not. And we were kind of interested to understand whether AI systems which were trained on 100,000 of these images are implementing the same rules. So are they kind of behaving according to medical textbook knowledge, which is the ABCDE rule, or are they solving the task in a different manner? And in order to answer this question, we need to kind of get a deep understanding of the system. We need to understand whether these concepts like symmetry, color, and border sharpness are implemented in the network, and whether they are used and how they are used in the prediction. So we need a component level understanding of our model. And we are kind of working since many years towards this component level understanding. So one of the methods which we developed like now 10 years ago is LRP. LRP explains individual predictions of the model of the neural network by redistributing the output backwards. So what you do is you redistribute the relevance, in this case what speaks for the dog, backwards through the network layer by layer, and in the end get a heat map showing you, visualizing which pixels, which areas in the image are important for the classification dog. But in addition, what you not only get this explanation on this pixel level, but you get also an explanation on the individual components, right? You see which filters, which neurons, which channels have contributed how much to the decision. And this is something which we will use later on. So basically, what happened then, which I call the second wave of XAI, is where people try to focus a bit more on the understanding of the model itself. So while with LRP, we were most interested of understanding predictions, understanding why this was a dog and this was a cat, here researchers try to kind of understand the individual components of the model. So for instance, what kind of concepts a specific neuron is encoding. And people propose techniques like activation maximization, where they kind of found examples which are maximizing the activation of a specific neuron, and by that kind of connected what is on the example with this individual neuron. So by these techniques, you can kind of visualize what concepts, what features an individual neuron is encoding. So for instance, here you see, like, this is from our demo, which we have like, looked at what some of these kind of neurons or some of these components are encoding of the network which was trained for the skin cancer detection. And you see that maybe for some of them are really focusing on shades of black or of things which are kind of uneven. So all these examples show images which are maximally activating these neurons. And you see these images have some kind of like Navi, which looks like cancer because it has very uneven color distribution. And these kind of few particular neurons are picking up this concept. Okay, and what we wanted to do in our work, which was published this year in Nature Machine Intelligence, is to connect these two views. So we wanted to connect these methods which were showing us what individual neurons are representing with methods like LRP, which allow us to compute the relevance of individual components for a particular prediction. So what we did is we kind of first collected these concept examples for every component of the model. So for every kind of neuron, what we did, we collected a set of images which are maximally activating these neurons. So these images are containing something which is encoded by this neuron because they maximally activate this neuron. This is step one. So we connected the model with the data. So we represented what components are encoding by examples, example images in this case. Then what we did is we used a clip model, or in this case, or a medical clip model, to embed these images into semantic space. So basically, while here we can kind of look at these images and ask ourselves what do they have in common, what we did here is we wanted to automate this process. So we kind of used a pre-trained model, like a CLIP model, to embed these concepts examples into a vector, into a semantic, meaningful vector. So this CLIP model kind of allows us to interpret what these individual components are representing. And in the last step, what we can do is for every prediction, of course, we can apply LRP, which kind of tells us which components have contributed to this particular prediction. So we connect kind of the prediction with the component by just using a method such as LRP. So kind of with that, we have I call it like a holistic understanding of what's going on, because we have connected the model, the individual components of the model, with the data, with the concepts examples which describe what these model components are doing. We use CLIP for interpretation of these components. And we also have LRP, which allows us to tell us which components are relevant for which task. And basically, what can we do with this approach? So what we have in the end is a component level understanding, because for every component of the network, for every neuron of the network, we have a semantic description of what concepts it represents. So similar to the airplane example here. And what can we do with that? We can search for components. So we can just ask, is there a component called watermark represented in the network? So why can we do this? Because CLIP models allow to a multimodal, they connect kind of the textual description with the semantic description, with the visual description. So we just kind of use the power of CLIP to Google within the model. We can kind of search for components, say, okay, is there a component which represents a concept watermark? And we found some components representing watermarks, and what you see here are these kind of example images which are maximizing the activations of these components. We can also describe the knowledge which is implemented in the model. So if you assume that you have like a vocabulary of concepts, then you can just automatically check whether these concepts are represented in the model or not. So you kind of just measure the similarity between this concept embed description vector and the visual vector which you get from this semantic embedding. And what you also can do is you can look for we call it the dark matter, so knowledge which is in the network but is which is not described by the concepts. So this can be maybe other concepts which you didn't have in the vocabulary, or this can be something else which is in the network but is not really captured by this concept. Okay, so what can you do with that? You can, for instance, audit models. So maybe it's not an audit in the sense as TÜV and other institutions define it, but we call it auditing. So you can just check whether these concepts which you define as valid concepts, such as like concepts related to asymmetry, to border, to color, are represented in the model and are used during prediction. And you can also check whether maybe spurious concepts like hairs or some red skin is used by the model. So you can do it in an automatic session without a human in the loop, because kind of CLIP there's a whole trick to automate this using CLIP. So we rely on CLIP to automate this process. And we can see that for this model, maybe there are some of the ABCDE rules are kind of used in the prediction, but also some spurious correlations have been picked up by the model, and which in this case maybe this model would not pass the audit, because it relies on some concepts which you don't define as valid concepts in the prediction. So it's not that these concepts are only like represented, but they're also used in the prediction. So you can kind of separate these two issues. Are the concepts present in the model, and are they used by the model? So we also have some methods to kind of not only to detect this, but to also tackle this problem, but I will not talk about that. So just a few words about our work, which is now presented at NeurIPS on XAI for LLMs. So basically, our goal is to tackle hallucinations with component-level understanding. So maybe I will skip this a bit. So basically, what we kind of came up with is the idea that you have in LLMs, you have this in-context learning, and you have parametric. A model can answer from parametric knowledge or from context, right? So for instance, if you ask an LLM how much dust is blown out of Sahara each year, it may be that the model has learned this during training, so it can kind of answer this question from parametric knowledge. Or if you have a RAG system or you provide some context, maybe this information is in your context. So the context could be, for instance, all Wikipedia documents which the LLM has access to. And what we want to do is we want to kind of ground the LLM answers in the validated context. If we assume that the Wikipedia information is valid, then we want to distinguish the scenario where LLM is answering from its memory, from its parameters, from the scenario where we can really say, okay, the LLM is answering because this information is present in this document at this position. And we came up with explanation methods based on LRP, which can do that very efficiently. So we can kind of pinpoint exactly to which part of the context the model is using when answering this question. If the model is not using the context, then the model is answering the question from parameter knowledge. So we can kind of at least distinguish these two cases, and we think that this can help us to be more certain about the answers. Because if the LLM tells us, okay, it's 182 million, and it provides a source for this answer, then we can check the source, and we can kind of have a grounding of the information. And it's different from, because you could also ask the LLM to say, okay, tell us how much dust is blown out of Sahara each year and provide some sources. But then the LLM made up some sources. This is different. This is really, we have this validated information, and we force the LLM, or force through the explanation process, to pinpoint which part of the information was used in the answering. It's not like a generated source, which can be problematic. So last slide. This was kind of one part of the paper. Another observation which we had is that in LLMs, there are two types of heads. We call it parametric heads and in-context heads. So we could identify attention heads which have kind of the role to retrieve information from the parametric knowledge. So they are only kind of dealing with retrieving everything about Sahara, for instance. If you ask about Sahara, so these heads retrieve all the information the LLM has learned about Sahara. And we have heads which are kind of processing the context, which are processing what you gave as valid context to the LLM. And by trading off these kind of heads, we can control how much the LLM is really relying on the context and how much it's answering from memory, from what it has learned. And we think that this kind of control can be very interesting for fighting or tackling hallucinations, because maybe you want, in certain scenarios, you want your LLM to really stick to the sources and not to make up anything new. And you can, to a certain degree, you can control it. Thank you very much.
Thank you, Wojciech. You just solved my biggest ChatGPT problem. Who wants to be Wojciech's question? Kerstin from TÜV-AI Lab. By the way, we have many colleagues of the TÜV-AI Lab here with us today, so do talk to them.
Hi, thank you very much for the talk, very interesting. It's been a while since I've been deep into the topic. That's why I was wondering, how well does the mapping work if you look at it from a component perspective? Like, if we go from each component of the neural network, how easy is it to map the features that they're looking at to each component? Is it like you have a clear map, or is it like everything is a bit vague?
I think it in the end depends really on the concepts and the data. So if you are talking about objects and parts of objects in visual concepts, then I think you can do this mapping very, very well. If you're talking about more abstract concepts, which are harder to grasp and which are maybe more global, but even global concepts to a certain degree you can map. But I think this interpretation can be then more difficult. And also, like a hard assumption which we make is that the LLM is able to understand the concepts which are kind of in the images. And so you have to make sure that you use not a clip model which is kind of trained on this data domain. If you use a clip model which is then applied to some radiology data or some other types of medical data, it may not be kind of able to understand this concept. So you should make sure that the clip model which is doing the interpretation is really understands the data. And by the way, what I forgot to tell, the first author of the paper is also sitting there, so Max. If you want to talk to him, he will tell you more details about the paper.
Thank you.
Let's have another round of applause. And Max.